So we start the second hour of the legacy session, and now there will be a presentation by Simon Gittig. Unfortunately, he could not come. He broke his arm and had to go to the hospital. But he recorded his video on the way to the hospital. Actually, two videos. One of them we already saw partially. This is a video about Gelfand mathematical work. It's 28 minutes, but I'm only going to play the first 5 minutes. And then David will so that video tells you about Gelfand Naimark works at the end of 1940s. Okay, so this is Simon Gittig.
I will say several words about the first period in Gelfand activity at representation theory. It was Gelfand Naimark cycle of works on unit representation of complex multiple groups. I was happy to knew Mark Aronovich Naimark, outstanding mathematician and a very nice personality. So we need to start from 1947. In this year, there were 3 different publications about unitary representation of Lorentz group. Papers of Valentin Bargmann, Gelfand Naimark, and Horocycle. The address was clear. It was physical hope to do something important for non-relativist quantum mechanics. Also, of course, SL2 its simplest semi-simple Lie group. But I think that physical connection were first. It was some things which were before. It was, for example, work Gelfand-Rykov about completeness of unit representations for locally low compact groups. Then there were examples of Dirac and Wigner of unitary representation of Lorentz group. But it's clear, in particular from Bargmann's paper, that consensus was that probably it's very difficult or impossible to give complete classification. Bargmann referred on Wigner, who thought that it must involve a very difficult or again maybe unsolvable problem of John Neumann's factors. And first thing which we can see, at least in publication Bargmann and Gelfand Naimark, it's a big surprise. The problem could be solved, and the answer is very explicit, very simple, as wrote Gelfand and Naimark. Formula looks simpler than in 4 finite dimensional representations. Of course, it had no sense to discuss priority problem, but anyway, it has a sense to compare a little different paper. In paper Bargmann, there was considered the real group SL2A, and as a result, he discovered a representation of discrete series. Of course, a very spectacular discovery. All 3 in 3 publications were given nice explicit formula and proof infinitesimal completeness of unitary this list of unitary representation, but I believe the Gelfand and Neumann went much more far. They constructed surprisingly a full series. All possible elements already there. Zonal spherical function, definition of character as distribution, formulas, well-typed formulas for values of characters on regular elements, and finally, so the proof, global proof of completeness, and what looks as most important, Plancherel formula. Analog of Plancherel formula for Lorentz group, inversion of non-commutative Fourier integral. It's surprising computation, about probably 10 page.
Okay, so now David will continue about this maybe later works. Just let's turn on the light. We have to put on the microphone.
Okay. So I come a little bit, so to say, to the beginning of Simon's talk. So before, so say, the war, before the Second World War, were essentially works on representations of compact group, the great work of Hermann Weyl, and so say the existence, completeness representations of a compact group. I think was more, I'm not historian mathematics, I can easily miss, but there was one really work on representations of non-compact group. There was a work of Wigner on representation of, so to say, Poincaré group. So it's a Lorentz group plus shifts. And essentially he classified the representations, reducible representations such as shifts x non-trivially. So there's more a small part was left. It's just to classify, understand representation of SL2. But as we know now, it's kind of the most difficult piece. Now, there was another theory developed by the late 30s, early 40s, was von Neumann's theory of kind of representation of arbitrary group. And von Neumann realized that in general, one cannot hope to describe irreducible representation because their factor representations often appear, and then the problem classification of reducible representations becomes unreasonable. So Gelfand, now, as much as I can reconstruct from what I read as his interview in Quant, it's actually the only real autobiographic piece, and from my memory of Gelfand, he was basically analyst with very good feel for combinatorics, which for him was part of analysis. And algebra was a tool, very important tool, but just a tool in dealing with problems of analysis. But so he really believed in his version of a beauty of mathematics. in his version of Beauty of Mathematics, would tell him the good groups should have good theory of representations. The same way a symmetric group or unitary group has good theory of representation, the same should be true for Lie groups. And so the main thrust of kind of the first period, what Sam talk about, of representation is to construct a nice theory of representations of Lie groups. So his first works with Nijmerk are on representation of complex groups. We know now that it's much easier than representations of real groups. You don't have discrete series. And in some sense, all representations sit in the induced representations. But the idea that you have to consider induced representation, a kind of geometry, what we think now as a sheaves, line bundles on a flux space, this was, I think, one of the main development of Gelfand. He realized that there is a way, geometric way to think about representations. This brings in something I'll pick up later, which was important for him as an analyst. There are two different ways to think about representations. You can think about representation up to equivalence. And originally, Frobenius' definition first was characters of representation. Or you can think about representations as a concrete realization when matrix coefficients as a functions on a group are important. And for Gelfand, interesting, he really kind of, his works an interplay between these two different ways to think about representation. One thing, and Simon mentioned it, he developed the notion of a character of representation. He realized it's very much related to this Gording space, which Kirillov discussed. He realized that you can associate to reducible representation a distribution in a group which is a character which plays the same role as a character for compact groups. In particular, they characterize representation. He also realized that in some sense, so for compact groups, the Plancherel formula, it means the way to write a delta function in a group in terms of, if one can write delta function on a compact group as a sum of characters of reducible representation, then one knows, then one gets all representations. So one way to see that representations which are constructed are all representations was for Gelfand to write a Plancherel formula, which we did, and kind of it is, he did it in the long computations for SL2. He has some kind of explicit characters he wrote. Then incredibly difficult computations for classical groups. And then he realized kind of a way to do it very simple, so they even formulate. So he kind of, and this actually was related to, reflects his analytic way of thinking, related to work on generalized functions. So you have a function in the group, and you want to find the value. And then you want to write as some kind of integral over a reducible representation of traces of representation times some It's a difficult problem. So Gelfand replaced it by another problem which relates to some work of Rees. You do the following. You take a conjugacy class in a group. You consider a distribution delta gamma of f, which is integral over gamma omega. You choose in some reasonable way normalize the measure. And then you consider limit of delta gamma of f when gamma goes to identity. Of course, this thing blows up. But if you multiply it properly normalized, so to say you take a distance of gamma to identity to the to some appropriate power, then it converges to f of a.
How would you want to put limit sign on the outside?
Okay, fine. That's important. What?
What is delta then?
Delta function. So, and then on the other hand, these orbital integrals you can, at least for complex group, write very easily in terms of character. So then you get some immediate Laplacian formula, and this also works somewhere for real groups, but for Gillen. So this is one line, and of course, study of this function, these limits, and so on, later became a question of p to the lambda, and it's related to work on generalized functions, and the Bernstein was explaining something of this in his reminiscence. So this is one line of argument. So to continue it a little bit, after works of so first of all, Gelfand worked only for classical group. He loved formulas and some kind. He couldn't write formulas. I mean, he didn't find a way to write formulas for E8, but he discovered for classical group what's called now periodic composition, a kind of so many structures which then when transported to the geometry which he discovered works for all semi-simple groups, but the methods we used for writing explicit formula did not work. So after working on complex group till 1950, by the way, Simon was slightly wrong in terms of dating. Actually, it's not important, but Gelfand, work of Gelfand and Nijmerk appears in 46 on Lorentz group, a year before the work of Bargmann and Hrisha. No, not important, but just they're independent work, so it's completely irrelevant. So after work on complex group, he started working on the real groups, and it was half success and half failure. He found a way to describe representations of GL and R, and because they essentially reduced to SL2R, they're kind no discrete. And he was not able to understand a discrete series. And the reason he was not able to understand discrete series is very much related to the way he thought about representations. He wanted really to construct representations. And so in discrete series, the simplest non-trivial example, okay, if you consider SL2R, you can construct representation of discrete series in an analytic function in the upper half plane. The next case is SU21. And there are three series. You can realize two of them in analytic function, upper or lower. And then something which you call strange series, which you could not realize. The realization came later through idea of lengths and the work of Schmidt and Atiyah in cohomology of line bundles, not in sections. But okay, these tools did not exist, and Gelfand did not think in terms of this kind of algebraic geometry. So he stopped. So this is one. Now, on the other thing which was developed in early 50s, it is his understanding the different questions of representations here, which seems to be unrelated, are really related. Now, this part is partially understood now, and partially is still a mystery. So one example, give his work with Zetlin on a basis, not, so to say, as I said, there are two different ways to think about representation. You can think about representation as classification of representation, or you want to realize your representation in some nice way, say the space of function or something else, and then the matrix coefficients become interesting functions. So he has his work with Zetlin on realization of special Gelfand-Zetlin basis for representation of GLN and orthogonal group. Actually, his so I have only one work with Gelfand, in spite of long interactions, constant interactions for many years. I have very few joint work and only one work on representation theory of kind of representation of GLN over periodic group, which grew from the thinking through his work with Zetlin. If you look to work with Zetlin and you see how matrix coefficients are written, you'll see there are kind of two parts. There is a relatively simple kind of, which takes more of a time, but then relatively universal part, which doesn't depend much on the parameter of representation. And there's a little bit of which depends on the representation. This is exactly what happens for representation of GLN. If you restrict it to what's called now merabolic subgroup, then it's standard. At least if you take not the general representation, it doesn't depend on the representation. And then you need kind of correction, something which depends, but very small part of representation depends on the parameter. It's what we have done there is just adjustment of his work for finite dimensional representation. Now, it is not clear to me why is it so. For example, we know that finite dimensional representations, the basis, okay, there's Gelfand-Zetlin base and there's canonical basing, base of Lustig, but we know the space of representation has a basis, very important. It kind of suggests the analogous thing should be true for representation of periodic group. It's clearly not yet understood. But another thing, when Gelfand understood very clearly, and it's kind of partially is a parallelism between questionist representations which happen, some duality or parallel. So let me give an example. I give two examples of phenomena which I think is not yet understood. It should be understood, but I don't know why people did not. So one is the following. You can consider two two problems. One problem is you want to understand the ring of spherical functions. So you consider representations, you consider representations, or finite dimensional representation of the group which have a, so you have a group G, which is real group. You consider finite dimensional representation. You consider representation which have a vector and so K is a maximal compact subgroup. You assume that this is non-zero. And now you can describe if you want to describe representations which have K invariant vector, it's the same as description of a space of a function related to the description of a space of the functions to sided K invariant functions. So you have this ring, the convolution. And now you study this ring. So of course the space GKK is the same as kind of positive part of a torus by Cartan decomposition. And now you can describe the function, which this ring. So here you have, of course, elements. So if you take element, let's call it nu here, then of course you can consider function h nu, which is to the delta function on k nu. Okay? And essentially what you want to describe convolution h nu 1, convolution h nu 2, and you write it as some integral of some function nu in prime, gamma prime, h. So you can easily describe the function geometrically. You just take the corresponding kind of a sphere, you convolve in itself. And so this, but clearly this function completely determines, the ring of spherical function. On the other hand, you can define another function in 3 variables. The reducible representations of group G are parameterized by highest weight. So you have representation pi lambda, and you can take pi lambda prime tensor double prime, and you can decompose it. The sum, it will be sum, direct sum of pi lambda with some multiplicity, which let's call it n lambda prime. Now, Gelfand observed, and I don't think that these two functions are very similar. What does it mean in his interpretation? It means the following. You can write system of differential equations, which such that this function is solution of differential equations. If you replace the differential equation by corresponding difference equations, then the functions n will be solutions of the corresponding system of difference equations. So I haven't seen kind of really good explanation for this phenomenon. All right, I give you one more example. This is example kind of on the space of representation. The analogous thing is true about matrix coefficients of representation. So here we're comparing multiplicity of representation and parameterization of representation. There is a next level when you consider, instead of multiplicity, you can consider matrix Clebsch-Gorton coefficient instead of multiplicity, and matrix coefficient of representations instead of parameterization of representation. representation. This is done only for SL2. And once more, nobody picked up the theorem. Few words about it. So here, if you have representation pi lambda, then it has a basis. V has a kind of a basis. C V lambda mu for SL2. So G is SL2. In the case of SL2, the spectrum is simple. So if you take representation that is strictly torus, that you have multiplicity is 1, so space is completely determined in the space of lines on which SL2, which are eigenfunction of SL2. So now you can consider V lambda prime tensor lambda double prime, and we can consider more precisely. Let me just not to mix, I write this E. Now you can consider E lambda prime, mu prime, tensor E lambda double prime, mu double prime. This is natural vector in the representation. And you can write it as a sum of some function T lambda prime, lambda double prime lambda, mu prime, mu double prime mu, of E lambda mu. Of course, there is a condition here that mu is mu prime, because of the eigenvector. So you can ask about this function. On the other hand, you can consider, let's consider representation. On the other hand, we can consider function. So finite dimensional representation of SL2 has invariant form, so we can take pairing between vectors, and we can consider the following function on G. Rho G, E lambda mu prime of E lambda mu double prime as a function on G mod T mod T. It's line bundle because this is eigenfunctions. I have E. Because E eigenfunction of the torus, this function is really a function of the double quotient. So, all right, I can, so if you take, it doesn't make sense for me to write, but if you take the book of Gelfand, Lawson, Shapiro, so it's a last complement there, tells you that these functions are Jacobi polynomials, and then can be written as kind of derivatives of power functions. You have an explicit expression, which you can read in classical book. And this function can be written as difference derivative of difference powers, which we know what it is. Just xn you write to x to the n, which is x next. So on this would have been. And equation, so the matrix coefficients of representation of SL2 are just obtained, just complete parallels, or continuous analogs of Clebsch-Gordon coefficients. Once more, this is a kind of symmetry, duality, which I have not seen anywhere. And this is one thing. All right. So by mid-50s, so let's say, Gelfand changed the interest inside of representation. He abandoned the representation of real groups, and he worked with Zeitlin. Zeitlin had concurrent died in the beginning of 50s, and he almost didn't have a long time, but essentially didn't continue work in this way on representations of finite dimensional representation. He moved to the study of automorphic forms. I think it was clear influence of Petetsky-Shapiro. And essentially all works of Gelfand on automorphic form, and they're all together with Petetsky. So there are a number of very important results there. And so it's the global and local. So maybe I first talk about local stuff as a representation of, okay, there are two, I'm mixing two things together, so let me put global stuff back. There are representations of, the work with Grive. Works of Grive were after, what? As Pasha told me 25 minutes. What? Oh, okay. 25 minutes, I stopped. I didn't look at the watch, I told him I will not talk too much time, so I didn't pay attention. So I finished in 5 minutes. So when you, so the works with Grive were works of different types of fields. He works with over representational group over finite fields, with kind of, after Green did description of representation of GLN over finite field, the first kind of serious work of arbitrary group and the Whittaker model is works of Grive on finite field. He worked with Grive and Petetsky, but I think this part of Grive on the representation of GLN, GL2 over periodic field. Now, here I want to say the kind of achievement there, which also people dealing with it now, but I mean, is that he wrote kind of explicit formula, beautiful explicit formulas, okay, I will not write them now, for the characters of representation of discrete principle, discrete series. It was able to prove Plancharel formula by just analysis of it. The main thing which, so to say, we're missing now is the following. When we deal with writing formulas, as Romo was explaining today, we consider, so to say, algebraically, if we think about field of, say, formal power series over finite field, the finite field we treat algebraically. So we write some objects which are geometric in this sense, but ramified and unramified extension for us are very different. For Gelfand, not. His formulas for characters of discrete series are the same in ramified and unramified case. And I think this is a kind of a symmetry which is important and which we don't know how to approach. Now, the last thing I want to say is just work on automorphic form. There are two main results. One is understanding that question of automorphic forms is question in representation theory. That's also representations which appear in the composition function on G mod gamma are the same which have gamma invariant functionals, a kind of Frobenius reciprocity, I think was completely unexpected to be a thing. And the last thing I mentioned is kind of a realization that one should be able to understand function on G mod gamma because Gelfand and Petetsky, they defined the space of cuspidal functions and proved that on the space of cuspidal function, clearly the most interesting part, corresponding operators have trace. So in principle, you couldn't compute trace. They did not, it was after work of Selberg who did it for SL2. but essentially before anybody else, and it's kind of beginning of trace formula in our approach. Okay, sorry for being over time. It is before. Not independent. Independence was not independent. It followed the final yes.
More questions? Okay. If there are no more questions, so let's thank. Joseph. So Joseph Bernstein is next. We do not have to start at 6:50. Nobody will eat and drink.
So first I want to make a remark. It's the last thing. So as I understand, so in automorphic, my understanding is that in automorphic forms, so there are two contributions. One is Gelfand realizations that automorphic forms, mass forms, and so on. This is just reflection of representation theory. And the second, Gelfand and Pisetsky-Shapiro, it's introduction of adelic automorphic picture. So I was asked to talk about works by Gelfand in representations of Lie algebras and some problems of linear algebra. So just I want to mention that in the paper of 1950, so he wrote a paper which is called Center of Group Algebra. So what we now call Center of Universal Logarithmic Algebra, where he describes the center. It was, I think in 1949, it was done by Horocycle, but this was independent work. And as I understand, the idea was that, that's my understanding, that when he worked with Naimark, and so he first worked with case of SL2, and so you have the Casimir operator or Laplace operator, and you can separate representations, but when you go to higher ranks, then Casimir operator is clearly not enough. And somehow there was no idea that there are additional central operators, and so he realized that there are such operators. So I wanted to mention this work. Okay, also David mentioned Gelfand Saitlins. Again, the idea was to try to write down explicit formulas. Okay, and now I want to say that if you look at publication, is that there are many works on problems of linear algebra, mostly works with Volodya Ponomarev. So it started, again, I'm trying to reconstruct how this started. So it started with ideas for the group SL2C. We would like to classify not only reducible representations, but let's say all representations, all representations of finite lengths. So, and you can see that this can be reduced to some kind of problem of linear algebra. For instance, for SL2, if you do it for SL2R, you should take, for instance, 0 weight 0, weight 2, weight -2, and then take these operators. This satisfies some very simple relations. They completely determine everything. So there's some finite linear problem which completely describes So it's a category of representations of SL2. And so they solve this problem for SL2, and then he Gelfand tried to understand, for instance, what to do for SL3. And so he first considered this representation, this problems of linear algebra. Suppose you have, what's the problem of linear algebra? You have some kind of finite number of spaces, finite number of operators and relations between them. And then you would like to classify these objects in some sense. So the idea is that he realizes there are three cases. There is case when these three types of problems of finite type, when you have finite number of solutions. What does it mean, finite number? It means that if you fix the dimensions of these spaces, then you have only finite number after isomorphism, finite number of such objects. There is tame and there is wild. Now, what does it mean, tame and wild? So his explanation is the following. So classical example of wild problem is that you want to classify two operators in, so you have two operators, so you have V to V, and you want to consider two pair of operators from V to V. And he explained why it is a wild problem, because in order to define this operator, you should write down n squared coefficients. In order to define operator B, you write n squared coefficients. And then you consider up to conjugation, so you said minus n squared. So it means that the problem will depend on, at minimum, you have n squared free parameters. Then he says that what's the difference here? You have 2n squared is n squared, so you haven't really gained anything if you consider. So for one operator, you have, if you have just one operator, then you have n squared parameters. But when you consider up to conjugation, you'll get just n parameters. So that's what his explanation. And now what is general definition of wild problem? Wild problem is a problem in which you can encode this problem of two operators. And for instance, so one of works by Gelfand Podmarev was that if you consider two commuting operators, you have A, B, V, commuting operators, then this problem is wild. Namely, what they show that if you have two non-commuting operators, two just arbitrary operators from L to L, then you can construct very explicitly some matrix of size 9 times dimensional, some space of dimension 9 times dimensional V, and two commuting operators, which allow you to reconstruct these two operators. So, and I think that origin of this is the following: that if you, they classified representation of SL2C. Now, if you try to classify representation of SL3C, then you have, for instance, the following representation. If you take torus and consider any representation, finite dimensional representation of torus, it's finite dimensional representation rho of torus, then you can consider induced parabolic induction. Pi is equal to induced of rho. Now, representation of torus, in this case, it is, let's consider SL2R. It doesn't matter. It's just torus is two-dimensional, so it is essentially two commuting operators. So, and the idea is that the induction doesn't, so to say, doesn't glue too much. So if two things were different, then after induction, they probably will be also different. So if you want to classify representation for cell to CC, then as a minimum, you have to classify pair of commutative operators, and they realize that this is impossible problem, this wild problem. Okay, so then, again, that's my reconstruction. So then they become interested in just problems of linear algebra in particular. They, so it was discussed here, problem, Kronecker problem, classification of pair of operators, V prime. It's Kronecker problem. And it's a slightly more general problem, classification of 4 subspaces. So here, L1, L2, L3, L4. So this is a tame problem. It's not final, but tame problem. And you can classify it. They had paper on this, and main, so say main tool of this paper was some kind of transformation, how from one such problem you can obtain another problem. Namely, you have such spaces, you consider direct sum of these spaces, you consider kernel entomorphism of V, and put it into the origin, and do some transformations. I will describe it a little later. So, and then when appeared paper by Gabriel, yes, by Gabriel, about representations of queries, that representation of queries will be of finite type if and only if it is Dynkin diagram, and moreover, that in the composite representation correspond to positive roots, then somehow he decided that this should be related to this, and really using some generalization of this construction, one can give. So Gabriel's proof was he just proved this, just compute this tame problem, so you can solve it. It's not easy, but it was proof without explanation, and we were trying to give explanation of this. And for this, we introduced this reflection factor. So if you have, for instance, if you have some source, V0, V1, V3, and then something here, doesn't matter. So then you can replace it and construct new thing which will be and construct new system which will be you replace at this place you replace the source by sink, where you write here V1 plus V2 plus V3 over V0, something like this. So you don't change these things. And here write V1 plus V2 plus V3 over V0. Yes. Okay, so this is some slight generalization of the construction. So the construction is that you make first this operation at this center, and then make similar operation in each of these vertices, and then you'll get Coxeter factor, which they used. Okay, and then, so this kind of operation, then at the time we haven't realized that it gives an equivalence in derived category, because I didn't know what derived category is at the time, and so on. So, but eventually it turns out that this thing gives equivalence in derived category, and this is the reason why it is interesting, and it has some many applications. And one of applications is that it gives some geometric picture for root system. And as a result, it was used by, precisely this kind of picture was used by Lustig in order to construct his canonical basis. Okay, so now I want to also tell some other directions of Gelfand work. So it started with work with Sasha Kirillov about division algebras for universal. You consider universal algebraic algebra, and you consider division algebra. So the idea was that, then Gelfand's idea was that it's difficult to understand all representations, so let's try to understand what's a generic point. And so they had some conjecture that this is, if you consider, I don't know how, D division ring, then it will be isomorphic to division ring of R and K. Some differential polynomial differential operators and plus some commuting variables. So this Gelfand-Kirillov conjecture, they proved some version of this. Namely, they considered, when they were proving this, then realized that you can do slightly different. Namely, if you consider space, basic affine space, which already appeared in Sasha Goncharov's talk, then you can realize U of G as differential operators on this space. In fact, you can add a little bit more, because on this space you have not only action of G, but you also have action of the torus on the right-hand side. So let's consider combination U of G and torus. It's called U of G tilde. It's slightly extended. It's finite over U of G, and it's very easy to describe how it is. And what they explain is that this is algebra. This algebra of differential operators on essentially rational variety. So it is its division algebra is isomorphic to R and K. But then Gelfand said the following idea that I don't want to consider one representation. So on affine space, naturally, if you consider, for instance, real points, then you get in functions of affine space, you have all the usable representations. And he said that let's consider, so here algebra U of G tilde, it acts on each of these representations. And he said let's consider all these representations, and the algebra of differential operators will act on all these representations. And this we'll call a series. A series of representations is the following: is some collection of representations in which you have not just action of this algebra U of G, but action of differential operators. Okay, and so it turns out that it's very interesting algebra, and as I understand, until now not too much known about this algebra. For instance, it's pretty difficult to show that this algebra is Noetherian, but it is. And it's difficult for the following reason. So when G is equal to SL2, then this algebra, then this A will be just more or less just R2, C2, just plain. So in this case, it is non-singular variety, so differential operators on it you can easily compute. It proves that it's Noetherian and so on. The problem is that when G is not of higher rank, then this A becomes singular. And it turns out that you cannot just say almost anything. Because here for non-singular, you can just make filtration and so on and reduce it to Hilbert basis theorem. If it's singular, you just cannot do anything. Okay, so now Gelfand Kirillov, they had some description of this algebra. And if you look at these descriptions, then in the heart of this description, you see the highest weight model, some universal highest weight model, universal Werner model. So after we worked a little bit with this, so once more, this is projects which have succeeded, maybe third succeeded, maybe 1/10 succeeded. So I think that this thing is, in fact, there is much interesting thing here. And later there were some works, for instance, for SL3. For SL3, you can try to do it over periodic field corresponding theory. It's all quite interesting, but not really done. Okay, so from this we can move to highest weight models, and so what we did with Gelfand, we understand these Werner models, and we formulated and solved the problem when you have morphisms from MK1 into MK2, and also realized, for instance, Weil character formula is very easy to prove using these models. And moreover, if you look at Weil character formulas, then Constant have rewritten it as multiplicity constant formula, multiplicity function, multiplicity of weights of reducible representation. So we have V lambda, and you are interested in dimension of V lambda mu. So he has written these multiplicities, but in, I would say, non-combinatorial ways. That namely, he has written not as the sum of some expression, but sum and difference of some expressions. And looking at this, it's quite clear that this should have, this means that this V lambda has resolution with Werner models. Just this is what this formula suggests. Okay, it's one thing, it's clear, and another is to prove it, but so eventually it was proven. So this is called BGG resolution. So it's proven that for V lambda there exists resolution M lambda, and so on. Okay, so and then, okay, so the next thing was yes. So in fact, the essential thing which we understood was translation factor, which was allowed to reduce problems, to move from one way to another and to understand. So this was the main technical thing. And then we understood that these models are part of some general category, which is category O. And this turned out to be significant introduction of significant subject. One of the reasons is that category O is somehow very simple, relatively simple-minded example of, so to say, some category of representation. So there are Hrocycle models, so they all look more or less, have about the same difficulty as category O. But in some sense, category O is very straightforward to describe. So as a result, this introduction of this category was very useful is, I would consider it as some kind of model category of categories which appear in representation theory, in different representation theory of groups. And okay, so on this model category, then there was question of multiplicities of reducible models, which somehow eventually it was formulated. There were some works where it was, first it was, we have assumed first that multiplicities are equal to 1. Then we managed to, it was in fact proven in Verma's thesis, and we couldn't prove it, so Gelfand got from somewhere Verma's thesis, and we tried to find what we don't understand. We found a mistake, and then we just constructed, just proved for SL4. It's not easy for SL4. We showed that multiplicity is not 1, and then Janssen developed some theory, and then, of course, you know that Kazhdan and Lustig came up with conjectures that something which they constructed using Hecke algebra, that this would lead to multiplicities. And then, somehow this was proven by myself and Sasha Berinson and by Kashewar and Berinsky. And this direction led to, was one of the directions of which led to development of geometric representation theory. So just I want to say that this category O, somehow it was, because it is very, in some sense very simple, on the other hand, it actually reflects a lot of structure. So somehow it turned out to be very useful. And I would say that for myself, that I wouldn't probably be brave enough to publish something on some category which nobody have seen somehow. But Gelfand told that that's the way to go. I don't know, don't remember. Just don't remember, that's all. Okay, so. Okay, so I think that's probably I will finish. So probably answering this question, probably all other letters were already occupied. That's the usual way how it went.
Yeah, okay, very good. Very good. So what I want to talk about is this here. And so to motivate this stuff, let me describe the background for it, which is the Poincare problem, something that David already discussed, trying to take decomposition of this space into a direct sum of irreducibles. And so one special case for which this is easy is the case where the subgroup H in question is the unipotent subgroup of this semi-simple group G. Then that decomposition is very, very easy. And so one goal in life is to reduce the general case to this very, very special case. And there is a stunt for doing that, which is known as the Horocycle transform. So what are horocycles? So in this general theory, let me remind you that X in that slide I just discarded is the group G over this subgroup H. And in that group, the horocycles are conjugacy groups of this particular form. And so you consider the collection of all horocycles. And the idea is that for various reasons, it's very easy to decompose L2 of horocycle space. So what you try to do is to reduce the general case to the horocycle example. And you do that by the horocycle transform. And so you take any space G over H, and then the horocycle transform of that space is given by this integral here. Since the decomposition of the representation on the horocycle space is sort of easy, if you can show that this horocycle transformation is injective, then you can reduce the Poincare problem for X to the Poincare problem for a horocycle space, which is easy. And let me describe how Gelfand and Gabriel succeeded in doing this. They worked out a beautiful theory for this horocycle transform in the case of SLNC, but I'll concentrate on how they work this theory out for SL2C. And I want to, I had a title to this talk of mine, which was called the Integral Geometry of Line Complexes. And what I'll try to do is show how the work of Gelfand and Gabriel is related to the integral geometry of line complexes. So let me talk a little bit about the horocycles in the case of SL2C. So we know SL2C is going to be complex matrices satisfying this quadratic equation. And the horocycles are the conjugacy classes, G and A. So what do these horocycles look like? Well, take the normal subgroup of SL2C itself. It's given by this equation, by this linear equation. So it's just a line on this quadratic. The horocycle, the N itself, is just a line on this quadratic. And if we translate it fore and aft by an element of SL2C, we get affine lines in C4 lying on the quadratic x1, x4 minus x2, x3 equals 1. So that's the horocycles. And alternatively, you can describe the horocycles by looking at the projection of C4 into C3 that just projects x1, x2, x3, 4 onto x1. And under this projection, the horocycles get maps to lines in C3 which intersect this very simple curve. So we've translated the horocycle transform into a very, very nice transform, a transform that takes lines in C3 which intersect this curve into integrals over those lines. And if you do that, then the Horocycle transform looks like this. Let's let S be the set of all lines having this property that I just described. And now consider every line in C3 of this form here. And let the radon transform be defined by the radon transform of F over that line is given by that very simple line integral. So this defines what is a very interesting radon transform, taking you from functions on C3 to functions on C4. Let me write down that transformation again. It's given by this formula here. By this formula here, taking functions on C3 to functions on C4. And it turns out that the Horocycle transform is just this transform restricted to this set of lines S that I wrote down earlier, the set of those lines that intersect that curve. So, well, what do you know about this radon transform taking functions from C3 to C4? It turns out it's injective, and its range is characterized by the following very simple quadratic equation. Now let me come to the beautiful, beautiful theorem of Gelfand-Vilenkin for line complexes. So now let S be any complex hypersurface in C4. And let's decree that this hypersurface is admissible if I take a radon transform and compose it with restriction to the hypersurface, and I get an injective mapping. So that's the notion of admissibility, and that's the theorem. Beautiful, beautiful theorem of Gelfand-Vilenkin. The assertion is that this hypersurface in C4 is admissible if it is a characteristic hypersurface for this partial differential operator. In other words, if you take the symbol of this partial differential operator, it has to vanish on the conormal bundle to this hypersurface S. And proof, well, here is a fake proof, but it kind of conveys the idea. It's that if S were not characteristic for this partial differential equation with respect to S, with partial differential operator with respect to S, then in order to recover S from its restriction to S, you would need to know not only the restriction of R of F itself, but you would need to know the normal derivative. Since non-characteristic, you need, for this quadratic equation, you need those two pieces of data. So that's a kind of a fake proof of this beautiful result of Gelfand and Garayev. And they also prove the following very beautiful companion result. And I'll end this talk by mentioning this companion result. So it's a complete characterization, well, with a few trivial exceptions, a complete characterization of all hypersurfaces in C4 that have this admissibility property. And here is the characterization. So this is the punchline of this talk. It's that it consists of one of two categories. The set of all lines in C4 which are tangent to a fixed surface, lines in C3 which are tangent to a fixed surface, or the set of all lines that intersect a fixed curve. And as you saw a few seconds ago, the invertibility problem for the Horocycle transform is of this second, belongs in this second category. Okay, I'm finished. You can start. Did I do it? Was that fast enough? I'm sorry. Please, no questions. I think you should start. Oops, one little question is how do you get this damn thing off?
Oh, there we have a specialist.
Ah,
Let me get this out of your pocket.
oh, we get that out.
Yeah.
Yeah.
Just going to use this. I'm suffering from asthma, so you'll be very pleased to learn that I can only speak for a few moments. And since we're trying to show the effect of Gelfand, this certainly illustrates it. Now, the interesting background, which is about all, this kind of summarizes the effect of Gelfand. I'll just say a few words. When I first went to Oxford and saw Tia, he asked me why the A-roof genus was an integer. A-roof genus was a combination of Pontryagin classes. I was busy thinking about something else. But finally, I came back to him and I told him that the A-roof genus was an integer because it was the index of the Dirac operator. And then I pointed out, because spinners, time spinners could give you forms, that you really got the signature, the Euler characteristic, and so on by that combination. So it was pretty striking that we got the index of Dirac giving you such great information. Now, that was pretty stunning, and what Tia and I felt was that really you could get at every elliptic operator by somehow using some form of the Dirac operator, or Dirac operator coupled to something, or some other geometric operator like Dirac. And we spent a very long time sort of, if I say this, fooling ourselves that really the only important operators were these geometric operators like Dirac. So it wasn't until Gelfand suggested in a paper that really you could get the index of a elliptic operator by direct means, and what you should be studying are elliptic operators and trying to prove their index in a direct way. Well, the fact of the matter is that eventually, with some hard work, Tia came to the States. We had a seminar with Borel. This was out at, I think, San Francisco. And eventually we did show that you could get the index of you could get a formula for the index of an elliptic operator. So that was all motivated by what Gelfand was trying to tell us. And you will find a proof of that in this wonderful book, which I owe to Melrose if he's around here today. I want to return to him. So now my voice has given up. I've been very explicit of how Gelfand has influenced us, and in a very, very positive way. Thank you very much.
Thank you very much. In spite I'm the last speaker, there are some Gelfand revolutionary ideas which was not mentioned. So I have something to say, but nevertheless I have some probably repetition, some comments to things which was already mentioned. Let me write down some list. Well, transformation. It was mentioned by Sasha Kirilov, but I want to say that this transformation, which brings the commutative algebra with involution to algebra of continuous function on some compact, revolutionary change the Fourier theory. Maybe it's forgotten now, but nevertheless, a very deep theorem like Wiener-Pitt and others becomes theory about commutative rings and obtain completely new proof which based on the main idea of Gelfand of maximal ideals. And this idea indeed was very beautiful, and I remember that when I was a student, it for me was some maybe first impression about beauty of mathematics. It's a very natural idea. And later, by the way, Gelfand told that if he knows in that time, if he knew in that time what does it mean prime ideal, maybe he called not maximal but prime ideals. And by the way, I want to say that his ability to look ironically on his result, which he obtained many years ago, it's very important. I think that because he changed often the topics, of course there are some topics which follow all life, nevertheless he considered his creative ideas in a sense very critical. It's maybe not so well known. Now another thing which was mentioned, sister algebras, and also I want to say GNS construction. Sister algebra is just a very nice notion for, again, non-commutative algebra with involution. And he was very proud, and he told me sometimes that unfortunately he had no possibility to speak to von Neumann, because if he can say to him something, he say that his sister algebra much better than von Neumann W star sister algebra, because it's close to analysis, close to smooth theory, and von Neumann more close to measure theoretical construction. As to GNS, which means Gelfand-Naimark-Siegel, this is we consider now as trivial construction, of course, because this is almost tautology, how to construct the unitary representation of star representation of algebra using positive functional. But in that time, it was, of course, a revolutionary idea, and up to now, we use it every time. Then, Gelfand settling basis. I think that this is very important notion, and somebody mentioned this, but I want to say that unfortunately, in that time, this, again, very important new ideas was not considered from more general point of view. And later, it becomes clear how universal this idea is, because we can consider analog of this basis when we have inductive limit of algebras, and so we can construct so-called Gelfand settling algebra. And this basis is nothing more than basis of the eigenvectors for these algebras. Then I want to say about the, this is Gelfand-Famin paper, which is also has some revolutionary idea with. This is about application of representation theory of SL2R to dynamical system. Gelfand has no serious paper about dynamical system, maybe except this one. But this is so important that the influence of this paper on theory of dynamical systems very long time. For example, what is about? We consider geodesic flow on the unit tangent bundle of the Riemannian manifold of constant curvature, and consider geodesic flow. And it was old object. It was considered before the war by Hopf, Hedlund, and many others. Even in Poincaré papers, you can find something similar to this. But many problem at that time was very complicated. For example, how to describe spectrum of the corresponding flow. Flow means the one parametric group, and it acts in L2 on this unit bundle of the manifold, and we can consider, can put a question, what's the spectrum of corresponding unitary operator? Unitary because geodesic flow preserves the Riemannian measure. And idea is very simple, and this is main point in this paper about, I think, 92. Instead of consideration of only one flow, let's consider whole group, SL2R. So in this case, we can immediately apply representations. We know representation of, we can consider representation of this group here. And after this, more or less clear how to describe spectrum of geodesic flow and Horocycle flow, and to prove that this is countable multiplicity of Lebesgue spectrum and so on. Later, this idea appeared in many papers. And by the way, I want to say one thing which is not so well known. Gelfand may be one of the first who considered systematically in this paper and propagandize this idea of the semi-direct product. If you have some action of the group on some space, on some topological space, and look at the space of function, you can consider semi-direct product of group algebra and function on this space. So this group algebra acts on the it's some people call in this way, and I prefer to this way. And this algebra, semi-direct product, obtained also representation, and really, even in this paper, this idea also used. And the representation of semi-direct product, one of the main methods in theory of dynamical system now. Now I want to mention more close to my interest. This is also close to me, but I want to say about the ideas which he suggested to work with him and with Graev, and I will mention his paper 70, probably 9, about what does it mean derivation of representation. And answer is very simple, and this is a result of his paper. So let's fix some point t0, and then consider the point t0 plus delta, and look at the representation of this local representation at this point. Say denote p t0, and then tensor product of pt plus delta conjugate, which isn't the same. And then you can consider the idea, what is the limit of such a representation of this type when delta tends to 0. And it's possible that there is a reasonable limit when you change the spin of this representation goes to infinity, and you obtain something which is really a representation of the first jet of these functions. So very nice idea, which show you that you can construct some kind of analysis on the group of current groups. And he put the question in 872, is it possible to describe the integral representation? This is derivative. What about integral calculus? And this is not so simple. And finally, we, with Graev, this is a paper, Gelfand Graev Vershik, 73, we describe such an integral representation for a group of rank 1, namely SON1, SUN1, and the real problem which appeared is very interesting, close to representation this group itself, not about the current group of function with the manifold with this value, but about this group. Namely, this is a problem which really discussed before, and it was some result by Dima Kazhdan, 67, yeah? And before considered some question by Constant. Namely, it happened that for these goals to construct integral representation, very important to understand the topology of identity representation. It's clear, what does it mean integral? This is infinite sum of very small things. And what does it mean multiplicative integral? This is infinite tensor product of very small representation. So very small means that we must consider neighborhood of identity. And it's really, it was known even from that time which people mention today, papers by Bargman, then Gelfand Naimark, and so on. This is the following. For SL2, for SN1, the topology is the following. So you have principal series, you have identity representation, you have complementary series, and it happened, and this is important, that really at this point you have not only identity representation, but another representation. I call it infinitely small in Leibniz sense, because it means that if you have a limit of complementary series, there is no Hausdorff topology here. You can't distinguish this representation, which is closed, an identity which is every time closed. But nevertheless, you can't describe the open two open neighborhood which is which have the empty intersection. So there is a representation which has the same, which is the limit of the series representation, which tends to identity. And it happened that in this representation for this group, you have non-trivial cohomology in this representation. I will not explain why this is important, but you can forget about current groups and to put the following problem, which is not solved even now. Let's consider arbitrary group and what's the topology of identity and for what representation we have non-trivial cohomology. There is a different possibility. For example, amenable group has the following property that even regular representation weakly contain identity. It means that you have almost constant vector in regular representation. In that case, you have one representation such the closure of this representation contain one. But in general, it's possible to have another representations which is far from regular representation, which has non-trivial cohomology. Up to now, it's not known, and there is a remarkable result laid by Yehuda Shalom and others, but nevertheless, it's a very interesting problem. And I want to mention one more thing, that Gelfand sometimes mention that idea consider only unitary representations very ancient. It's better to look at the more general class of this representation. And by the way, just now we tried to understand what happened when there is a Kazhdan property in which identity representation isolated in the space of unitary representation. But nevertheless, there is a non-unitary representation, and probably all this idea can be applied to non-unitary representation in the same time and cohomology. I want to mention only one thing in conclusion, that we must remember his co-authors, especially some of them mentioned now, but of course his papers were prepared by his co-authors who translated and make more, maybe reach some his idea. First of all, Naimark, then Shilov, Raikov, who study commutative algebra, Narmirta Ringa, well-known papers, then Vilenkin, and of course Mark Iosifovich Graev, who is still very active, and he lives in Moscow, and we continue the activity with him. And all these ideas, and I think that this conference, very good illustration how rich was his look on the mathematics, how fruitful was his idea. And of course, for this session about legacy, we need even one conference, not one session. Thank you very much.
So thank you very much. This was the last.
Questions?
Alan Khan is sort of standing on the shoulders of Grothendieck and all the C-star algebra. Does Gelfand have anybody know Gelfand have any